Hi, Boby.
Hi, Chinthaka.
So yesterday we gave a brief overview of electromagnetic sensors.
Yeah, you showered with equations.
But at the end of the day, I think we all saw that the equations might look scary, but they're really not, right?
Yes.
And they actually show us a lot of give us a lot of information really about electromagnetics. So the last slide we did, we talked about different types of magnetic sensors.
Correct.
Now, you probably saw one of those sensors had a very wide range.
The search coil.
The search coil, right? And also, when it came to the applications, it was used in a lot of applications. So today,
we'll discuss that.
Let's talk about search coils.
Yes,
right?
I'm
because
curious.
It's obviously wide range and
maybe it doesn't require complicated manufacturing process also.
That's interesting you say that. Now, initially, I think as we go along, you might think that, it's actually very simple to design something, a search coil. And I don't think it is simple. I think the principle is simple.
Yeah.
But I think if you want to design a really good search coil,
Mm-hmm.
there are certain variables and parameters that you need to consider.
Okay.
But before that, just to kind of ease into coils, I remember yesterday, the first thing you said when we talked about magnetic fields and currents, you said, can we, if you put a current through a coil,
correct,
you'll get a magnetic field.
Yes.
Right? And see, one of the most, I guess, common devices or tools you can build is something called a solenoid. Right? So here you have a coil, right?
Yeah.
And similarly, you have multiple turns here.
Yes.
Now, if you send a current through it, you will create a magnetic field. Now, if you look inside the coil, you'll see that the field lines are very kind of
somewhat uniform,
parallel to each other.
Yeah.
Okay, so by applying a current, you get a uniform magnetic field inside the coil. And if you think about such a coil, it's used in a lot of applications. In fact, if you look here, right, you can see there's some fluid here.
Okay.
Or liquid or fluid. And here you have a plunger. Here you have a coil.
Okay. It's not a spring.
And here you have a spring.
Okay.
Now, you can see that the cap of this plunger is preventing this fluid to go into this section. Right? So if you say this is section 1, section 2, right, there's this plunger that's preventing the fluid going into the next section.
Yes.
Now, this coil is connected to some, let's say, some electrical circuit. Okay. Or power supply. Okay. Now, this plunger, right, let's say it's made of a material that somehow responds to a
magnetic field.
Okay, right? So it could be some kind of a metal, steel,
some or soft iron, some magnetic material.
Now, when you provide current to this circuit, there's going to be a magnetic field. Okay, as we showed in the previous slide, right? So what's going to happen to this plunger now?
So it will get attracted.
It will move up.
Okay.
Right? So you see this spring is now also compressed.
Yeah.
And then it opens up a path for the fluid to flow.
Okay.
From section 1 to section 2.
Oh. So it's an actuator.
It's an actuator. So I think students who are doing this course, sometimes they might be a little bit confused, the difference between a sensor and an actuator, right?
Yeah.
You will see if you go to Google, if you type sensors, sometimes you also come across websites that talk about actuators.
Yeah.
So this is a little bit different, right? Because this is actuator is kind of performing some action, right? When it's because it's like a response to an input. Here we are giving
like you have mentioned here. Yeah.
Right. So it's a little bit different. But I was thinking, but we are not really sensing anything here, are we?
I see some dials there.
There are some dials, right? But what if I told you now, I cannot think of an application, but imagine now the electrical circuit is connected to something here.
Yeah.
Let's say it's a black box. We don't know. But the input, right, signal to provide a current to the coil is given by this black box.
Yes.
Now that depends, let's say, on detecting a certain magnetic field.
Yeah.
Right? I mean, I cannot think of an application, but let's say this depends on a change in B. Right? Here you have to sense this change, this magnetic field, and based on that, it will provide a current to the coil and the liquid will flow now from one section to the other. So my question is, we've done Maxwell's equations, right? Can we use the same coil? Like here we are giving the current, right? But can we use the same coil as a sensor?
Yes.
Is it possible?
Because I think the inductance of the coil will change depending on the position of the plunger.
Yes.
Suppose if you want to sense the position, it could be a way to.
Exactly. Yeah. So if you want to detect something, right? The same coil, technically, according to the equations we studied yesterday, can be used.
Correct.
So how would that work then? Here I've shown here the same coil, right? This is what we showed before. It's actually producing magnetic field.
Yeah.
But let's say that magnetic field, let's say it's a change in magnetic field. We're giving, let's say, a variable voltage.
Yeah.
Can you actually sense that magnetic field with another coil?
Oh yes, definitely. Like yesterday, what you explained is the magnet is moving and then there's a coil.
Yes.
Now the magnet is physically fixed, but it is excited using a sinusoidal current.
Yes.
There's a time varying magnetic field.
Yes. So it could also just be a simple coil.
So there is a dB by or dou B by dou T.
Yes. So that means that we are talking about the induced voltage, right? So in this case will be, let's say, minus. Remember the minus, right?
Yes.
And yesterday you talked about a flux. Remember?
Yeah.
Changing over time.
Yeah.
Okay. Now, when you talk about the flux density, you have to consider the area also, right?
Yeah.
dB dt over an area. Then you have minus mu0. Now, another thing you said was B.
What is that small n? Number of turns?
Oh, yes.
Okay.
Number of turns of the coil. Yes. Good. Good that you mentioned this. Yeah. So N is the number of turns of the coil.
Yeah.
Right. So
Phi is the flux lines.
Flux. Right. But then now, if you're talking about flux density, you're talking about area.
Yeah.
Right. Flux density over area.
So phi and B, Bombay B, is how are they related? I think yesterday we discussed this.
Yes.
B is equal to phi by area.
Yes. Right. So then we have something like this. Now, another thing we discussed yesterday was, we know that B is equal to, remember, mu into H.
Yeah.
Now, if you assume that there is nothing in between this coil, simply air, right? You can say V is equal to, exactly, mu0 H. Then this equation then can be written as V is equal to minus mu0 N A dH over dt, correct?
Yeah.
Yes?
Yes.
Yeah. Now, we talked about applying a time-varying magnetic field, right? H, T, right? Something like this. So, perfect, but magnetic field and time. Now, if it's varying as a sinusoid, right, then you should be able to write, now B and HI interchangeable, right?
Yeah.
With mu 0. Then you can write B is equal to Bm sine omega t, right? Where omega is here 2 pi. Now, then Vm you can also write as minus 2 pi n AF Bm.
AF is?
So, F, not smaller, F.
Okay.
Frequency.
Okay.
Right? So here the frequency of this time-varying magnetic field. So,
Or the maximum value of the induced voltage.
maximum value of the induced voltage, it can be written as something like this. Now, what do you see here, Bobby? I mean, from this equation, what can you derive? What can you what kind of things can you kind of understand from this simple equation?
So, by measuring Vm, I know what is the B at a particular frequency.
Okay. What else? If now, let's say you're a sensor designer.
Hmm.
You're designing a search coil now.
To measure B?
To measure B.
Okay.
Then, what kind of things would you consider looking at this equation? Now, you want to optimize VM, let's say.
Yeah.
Then
I would like to, I need a measurable output voltage.
Yes.
For a range of B that I am interested.
Okay. Now, if you're designing it, what kind of...
So, for the lowest value of B I want to measure, I will see what's the number of turns that I can set and area of the... A is the area of cross-section of the coil.
Yes. 2 pi r. Yes.
Yeah.
Cross-section of the coil. So, you would require a large number of turns.
Yes.
You would think.
Yes.
Right. And you said something about the area.
Area also, if it's a probe, which depending on its application, I can't have very large area of coil just for sensing purpose. So, there will be limitations, practical limitations.
Right. But ideally, you would want...
Considering usability, etc.
Right. Consider the use cases.
Yes. Yes.
Okay. So, those are the two main things
Yeah.
that you can derive from this, right? So, number of turns, ideal large number of turns,
Yeah.
and large active rate.
Yes.
But then is that it? I mean, is it actually that simple to design a search coil to get a maximum, output? Or the other things we need to consider?
Yeah, if the coil is ideal like this, then this may be enough.
Right. All right. So as we go along, we'll see there are more things that you need to consider. So I think one of the reasons that it's used in so many applications is because, okay, the wide detection range. But also, I think if you think about it, anyone can design a sensor like this, right? It just requires a coil. But I think, again, as you said, it depends on the application.
Yeah.
Right? So for certain applications, you might want high sensitivity or high resolution. In that case, there are more things that you might have to consider when you're designing a coil like this. Okay. And another thing, the output. By looking at it in the back end, you somehow have to integrate that, right?
Oh, if you want the B of T waveform, Bombay.
Yes.
Yeah. But if you want only the peak of, if it's only BM that we are looking for, then integration is not required.
Yes. But then if you want the output, right, that relates to the discharge.
Yeah, because what we have is the voltage waveform.
Yes.
If you want the B waveform, of course, we'll have to integrate because it's V is obtained through the differentiation.
Yeah.
And it's dou B by dou T.
Yes.
Yeah. Yes.